again, and always review, right? So let me start with reviewing Maxwell relations, and I'll do that with these things you definitely need to know. Now, I think the change in U is something you really got to have by heart. Not that it's not on the cheat sheet, but you got to recognize heat and work, right? Now, I've been doing this 10 years, that helps. But I do recognize heat and work. Work, unfortunately, has a minus sign, which is always a bit of a pain. And then we do Legendre transform, which I'm sure I'm going to ask you to do a Legendre transform on the next test, probably the final. Now, I am not beyond to prevent you from showing up with your calculator full of equations or just trying to straight up memorize it, which will almost guarantee to fail. I might come up with different equations, different letters to ask you to do Legendre transforms to see that you actually know this. And the formula, of course, is on the cheat sheet for the Legendre transform. Regardless, I know that 10 years, I do have this in my head. I know that enthalpy still depends on entropy, but it actually is dependent on pressure, not volume. And so, yeah, I've got that memorized. Remember the Maxwell equations. I'll do the others in a second. Remember the Maxwell equations are the it's actually, I actually was looking this up. I made a mistake. It's not Euler's criteria, it's Euler's test. Euler's criteria is some crazy difficult theorem in deep mathematics. Euler's test is the double derivative of exact differentials doesn't matter. Again, we went over that last time. But remember there's a very, very simple way to do this. What is it? Outer, inner. Right, so therefore, dt, and remember that these are, dt, dv at constant s is, and then inner, outer, psv minus dp, ds at constant v, right? And remember the utility here is that there's often thermodynamic derivations, that you'll get stuck and this will unstick you. And I'll do this one as well. I heard that. Let's see. And I can just look at it. dt, outer, dp, inner s, dv, inner, ds, outer, at constant p. Okay, now recall that next down the ladder is A. I like to start everything. I think about U all the time. U is the foundation of all thermodynamics, the equivalent theorem. Don't forget that one. And I know that A leaves work intact. Instead, it monkeys with the entropy part, which it doesn't like. So that's SDT. So A depends on T, and it leaves the work intact, and then DG actually is the ultimate Legendre transform, dependent on T and T and P. And tell you what, I won't write those Maxwell equations down. You had it from last time. Again, it's very trivial. And I always do, one thing I do have in the back of my mind, I always remember that the partial of A is always negative, fully negative. Partial of H is fully positive. Don't memorize that. I just have learned to recognize that over the years. Whenever I'm writing these down, if I do make a mistake, that usually is how I spot it. Or look at the answers in the back of the book. Now also recall that each one of these, the reasons we have 4 different energy functions, that each one is useful for different things. Remember that U and H at constant, U at constant volume is heat, and we power the world with heat. H is more practical because at constant pressure it's heat. We live in a constant pressure world. It's very dangerous to do things at constant volume. The Earth is not surrounded by a metal box. It is a constant pressure system. So H is heat under that circumstance, as you learned in high school. Okay, A and G. You probably haven't heard of A, but A is the maximum work at constant temperature. The maximum work out of the system. It's reversible work at constant temperature. It's easy. Just wipe that out. Now this is where this is a little unsatisfying. Like, you know how the rules of U and H switch depend on what's held constant? A and G don't. Both of them are actually maximum work. They're both reversible work at constant temperature. And you don't have to do that little switch that you do here. And you're actually going to prove that on the next homework, that actually plus VDP is the same as minus PDV. That's on your homework. It's a fairly trivial exercise. I even actually did it in class. on that extra hour last Friday. Now, also don't forget the ultimate utility is that energy is easy to measure. I've got all kinds of insanely accurate energy meters, but entropy cannot be measured, not at least directly, not that I know how. So, but entropy is the only thing that actually matters. Entropy decides whether the reaction works or not. And remember, if you're out of here, and if you go to work in a giant chemical plant, if you can make the process more efficient, and that would be making delta G more negative, what you're really doing is increasing the entropy, and that would be worth millions, if not tens of millions of dollars. Just 1 or 2% changes of efficiency in like a giant chemical process matters unbelievably large amount. So, knowing that increasing total entropy is the most important thing in the world, that's why these energy functions are ultimately very useful, because they actually tell you that just under certain conditions. So at constant volume and entropy, a negative change in U is total entropy increasing, which is good, except that I'm not sure how to, keeping constant volume is dangerous. Okay, reversible adiabatic, but actually reactors don't work that way. That's, if you're an engineer, you know what I'm talking about. Anyway, people are not at constant entropy, so no. Constant pressure, constant entropy, the constant pressure is better, but again, no. So A and G are more useful. Constant volume, constant temperature, negative A is positive total entropy, and yada, yada, yada for G. So, and remember again, I can't measure total entropy directly, but I can measure these, and it works. So that's why I'm worried about DG. Okay, last time, this is where I kind of started getting a little tongue twisted. Now we're going to forget about constant entropy, constant volume, because it really is not that important, which is why we told you DG was everything. And what I want to do from now on is get to manipulate G's, because I'm in a constant temperature pressure world. I want to manipulate G's to make it work, to make the reaction go. Whether it's chemical or biochemical, it's not important. And what's nice is that, okay, this guy, manipulating G is easy by manipulating pressure. This looks very equal, right? Therefore, DG is, we're going to be doing gas reactions, and it looks like I can manipulate the G of every chemical by just modulating the pressure, and I can. However, it's not practical. So again, you're working for a chemical company, you're producing ammonium or something like that on a hundreds of millions of ton level. You want to manipulate the G's, you want the G's of the reactants to be high, you want the G's of the products to be low. This is a great tool to do it. It's an easy tool, it's sensible, it's just do it on your calculator. However, manipulating pressure is dangerous, right? We don't like to do anything. We don't like to manipulate pressure inside of large vessels. Probably you're going to be at high pressure and boom. Another thing is that, well, maybe you're manipulating some chemical reaction on a hundreds of metric ton scale. Maybe it goes to low pressure. Maybe that drives the reaction. Problem. Pumps are expensive. So again, if you're producing some giant bulk chemical and raising the G of reactants, lowering the G of products means less pressure, it's expensive, and no one likes that. So you know that what you really do when a reaction doesn't go is generally you heat it, and you're going to understand why in a second. Generally, temperature is your control stick, because, that's incredibly easy. But the problem is it's equal to minus S. So make sure that's where I had some problems last time. It's equal to minus S. Now, I do know that S is always positive, and it's something that we're going to really go over today. So I know that raising temperature will lower G. That's all fine and good, but reality is what you really want is, remember for a reaction, so this is for an individual substance, so I want to remind you for an actual reaction, what you're looking at is that delta G of the reaction minus delta S. And of course, what I'm talking about is just do A goes to B, right? Because that's obviously very trivial, and therefore G of B minus G of A is delta G, which you want to be negative, or why are you doing this? If it's not negative, that's ridiculous. You want this to be negative. You want to know whether you want to drive the temperature up or down, because it matters. If you're not going to do pressure, it's too dangerous or expensive. You're going to manipulate temperature. All right, you want to see that guy turn negative or more negative. But the problem is that when you try to manipulate the G at each one of these, I don't know that you can do them separately for practical reasons, right? But anyway, if you want to see whether this is more negative, what you actually got to know is the change in entropy. You can do that, and I'll show you how to do that. But again, practically, it's a Bismarck. Practically, I don't have entropy meters, but I do have enthalpy meters. And that's the point of the Gibbshelm equation. So I wasn't, my crazy stories, I kind of ran out of time and I was rushing. Sorry about that. But so let me redo this. Now that I hope I'm kind of motivating this a little bit more. Again, we're not going to mess with pressure because that's way dangerous. The body, cells, proteins interacting, you do not crush cells under an anvil to change their pressure. All right, you change temperature because that's easy. But now I've got this problem that it's minus the change in S, and I've got no good meter. Now let me remind you, if G is actually U plus PV minus PS, but anyway, you should know that's H minus PS. And therefore, you solve for S, actually solve for minus S. That's where I was kind of screwing up last time. G over T minus H over T. Okay, so that's great. I've got that sucker in there, and therefore, here, I'll do it up here. So dg dt constant P. I might forget the constant P sometimes. It kind of doesn't matter. Well, it does, but anyway, whatever. So this is G over T minus H over T. And again, the problem is that in terms of getting something like G is CV ln TF over TI. No, that's not right. Don't write that down. But anyway, I would like to solve a delta G is CV ln TF over TI. I would like to solve something like that, but I can't because I got to have the G's on this side. I need to have dg over G and dt over T. I got to have that. I can do that with the T's, but I can't do it with the G's. I got no good solution, so I am stuck. Now remember that this is an example of two derivations mixed into one. And yeah, I kind of hate that too, but I don't know of another way to do it. So I'm going to just crazily write this for no reason and just leave it. Now Gibbshelm is kind of this clever trick where remembering that the ultimate goal is, does it go up, does it go down? I just want this reaction to go. I want negative G. I want to know, how do I change the temperature? I don't really care how much. I just want up or down. If you just want up or down, here, let me remind you that we're stopped right now. We're done with this. We can't do it. What Gibbshelm figured out was that if you do this, so if we can do this, if we can figure out what the change in G over T is with respect to T, up or down still works. And that's because there is no negative temperature. So if the change in G is still positive, then the change in G over T is still positive. Negative, right? Because positive don't switch up or down. Now let me remind you that you have to do product rule. And so, let me cheat up my notes. Leave one function alone and do the other. Okay, this is a constant P. I do need to keep that. Leave one function alone and do the other, and then do the opposite. T squared, and that's just a G. So I don't want the notation to be confusing, right? There we go. Which is, I'll just factor this one out of T. dg dt constant P minus G over T. Okay, now you've already solved for this up here. So, and again, I'm just repeating what I did last time, but I was going way too fast, so let me make up for that. So there's that. Now, so let me actually summarize that, but not doing it with G over T. Let me remind you, when this A goes to B, we only want delta G. So actually this does require, I know it seems like kind of trivial, but I'm writing the change in absolute G over T is equal to, the change in absolute G over T is equal to minus H over T squared. I'm just kind of inserting a delta into that. I want to let you know that that's not trivial, by the way. It does require a separate derivation that actually goes identically, but you can't necessarily just throw in these deltas. I just did it, but I just want to remind you that it does take a little bit of extra work. I did it once, and I don't feel like doing it again because it's kind of BS-y. But anyway, okay, so there you go. Now again, does it go up, does it go down? Let's see, okay, side delta H. Okay, let's see, let's make delta H negative, then all of this is positive, right? So remember, this is actually why I'm always trying to beat you over the head of is it up or does it go up, does it go down? This is why, because it matters in this case. Okay, so if temperature goes up, does delta G go up? In this case. You should be able to read the derivative, right? This is on net what? Net positive or negative? No, it's net positive. So if T goes up, delta G goes, what does the T do? Nothing. All right, now T is changing, right? You see why this is a little bit of a cross-eyed thing? T is going up, so this looks a little bit funky, but remember, T is always positive. Right, it doesn't matter if it's going up, it only matters if it's positive. So delta G is positive. Okay, so now this, of course, is this exothermic or endothermic? It's exothermic. Now here's how you remember the energy bank. Remember I covered this about a month ago. If you're compressing the gas, you're storing energy into it, right? So energy in is positive, right? It's positive to store energy. That includes heat from the outside. Okay, if it's negative, then you're losing heat. Now that, of course, if I'm touching the magic cylinder, it's hot or cold. Touching it, delta H is negative, is it hot or cold? It's shedding energy. It's hot, of course it's hot, it's shedding energy. Of course heat is energy. All right, so then let's do this one. Okay, so actually, hold on, let me back up. Okay, so exothermic reaction, you want it to go, should you heat it? Right, no, you should not. That will make the delta G go more positive. That's bad. Okay, delta H is positive, then the exact opposite happens. Now, another way to do this, by the way, if I ask this, and I'm pretty heavily leaning towards it, is in this case, let's do A goes to B. Let's do the first case, which is negative H. Remember that would make heat a product. Okay, if you add heat, let's say that, sorry, that would be a little bit ahead today. Okay, let's say that there's some equilibrium, and heat's a product, and you add heat. What happens to the equilibrium? Shifts left, right. Like the Chatelier principle. Okay, so in this case, which again, this is the case I just added, heat is a product. If you increase the temperature, which is adding heat, you're going to get a more positive delta G, which is bad because the equilibrium will shift to reactants, which is bad, right? Right, it makes sense. So again, if you have trouble walking, if I ask you this and you have trouble walking it through in your head, just do this. Just get which direction the heat belongs to, which is something we've been covering for over a month now. And you can figure out, you figure out whether it's good or bad. And remember that negative delta G's, we're going to call those good because they make reactions happen, or what else are you doing? And yeah, get on which side, figure out which ways it goes, and then justify it, figure it out after the fact. Figure it out, giving that you know the answer, okay? So anyway, just testing the strategy. All right, now, next thing, I'm still actually reviewing, like an idiot, but I really felt like I did not cover this nearly as much as I should have. Okay, so not on this homework, but the next homework, I want to go ahead and give you some homework hints. This one is something that I kind of latched on to a couple of years ago, something that engineers do. And so some engineers once asked me in class about some of the things they were doing in engineering class, and fortunately I'm quick-witted enough to be able to answer them. And then I, of course, formally incorporated their question into the today's lecture. So I can tell you who did that so you can get them. So what you can do is, now remember that I solved the derivative, I solved all these partials, and you know that's part A. What's part B? Part B is always the integral. Okay, so let's do that. Let's the g over t. Sorry, I didn't write that well. Okay, so we're going to integrate the g over t, and that's minus delta h. Oh yes, sorry, delta g. I want to put this in terms of reactions, because that's more sensible, right? And that's what you care about. Okay, so all I did was I just juggled the partials, just split them up. And again, you see why this is important, because now this is solvable. Okay, now remember that the limits have to be the same, the limits have to be the same thing as the partial. It just doesn't make sense otherwise. So this is delta G1 over T1. So remember, we're changing the temperature. Sorry, you know what? I should have started over here. Should have done this one. This one's easier. So we're going to start at T1, we're going to end at T2. Why? Because I'm changing delta G as a function of T. So this guy is easy, right? It's only temperature, starting from the initial to the final temperature, T1, T2.
T squared.
T squared, yes. Right, that matters. That was your point? Yeah, thanks. Sorry about that. Yeah, I'm kind of going to start making mistakes. Okay, so sorry, right? I should have started here. This is easy. This is blindingly easy. Okay, now again, the limits need to match. So this is the initial G given the temperature that, you know, obviously this is going to be 298 degrees, right? When you do your homework, yeah, this is going to be 298. And this will be some higher or lower temperature. And there'll be some G2, delta G2 of that. Anyway, so blah, blah, blah. Okay, Gibbs-Helmholtz integrate to get finite values. What I want to know is delta G at a different temperature. That'll be G2, delta G2. That different temperature will be T2. Now I solve this, which is, I know, God, that actually looks horrible, doesn't it? It's really kind of shockingly easy. Delta G2 over T2. Minus delta G1 over T1, so I'm going to set that to the other side. Now this would be, now remember your Hess's law, A goes to B and B goes to C. Here's the delta G's, what's the net for A goes to C? Again, high school stuff, you're going to do it next time. This is 298, and this is from the table in the back of the books of delta G's of A and B, or methane and oxygen and all that stuff. And if you don't remember it, you're going to see it next class. Okay, now what I'm doing here is I'm going to actually treat delta H. This is actually the answer to one of your homework questions. Not this next one, but the one after. That one's kind of hard, by the way. If I take delta H out, assume that delta H is not temperature dependent, then what I get is this. And so I'll call that H1. So again, I have those tables in the back of the book with delta H and delta G and S and all that of water and methane and oxygen and and those are all numbers, delta H's and delta G's at 298, which will be T1. All right, now I'm going to bring delta H out, so that's delta H1 again. I have that from the tables in the back of the book, and what I end up with is 1 over T2 minus 1 over T1. Okay, so this is where it's useful. Again, tables in the back of the book have given you this, and then I said, okay, is this spontaneous at 298? You just do your high school homework and you say no, it's positive, that's bad. And because it's endothermic, I'm going to say at what temperature? What about at 300 degrees? Not K, that doesn't make sense. 300 Celsius. So you put in 573.15. Plug all this in. You solve for that. Hey, it's negative. Oh, there you go. So that's a reaction that you heat. Kind of trivial, all right? But now notice, and again, I'm giving you an answer to homework, that I had to bring the delta H out. To write this equation, I assume that delta H is not temperature dependent. Is it? Does delta H change with temperature? Does it? Yes. Remember, isothermal. Delta U, delta H are 0. You write that down instantly. Hopefully your kind trained you to do that, so you instantly get points. But under adiabatic conditions, you need to figure out the change in temperature, and for H, you multiply that by the heat capacity at constant pressure. The point is that the delta H is not a constant with temperature, so bringing it out of the integral is a mistake. And answering one of your questions, by the way. So this is an approximation. It's a very simple approximation. What you're also going to do on your homework is that you're going to figure out that if delta G1, again, this would be at 298, is delta H1, again, 298 minus 298. If you plug this in, what you find is that delta G2 is actually delta H1, again at 298, minus this new temperature. Okay, so what this is, what all of this comes down to is, again, high school level delta G questions where you change the temperature. But you made the approximation of letting both the enthalpy and the change in entropy to not change with temperature. All right, again, that's a high school level type of approximation. You learned about delta G in high school. You learned that those numbers in the table at the back of the book were at 298, and if you change the temperature, you just did this. The problem now that you're a senior in college, the next derivation, which is going to take you a really long time, is that you're going to let H and S change with temperature. And that's, I forgot. Anyway, we're going to cover that actually on Monday. So, yeah, just to remind you, connect you back to hopefully in high school and yada, yada, yada. Okay, some new stuff. Gonna just cover one thing pretty quick before we get to Hess's law, and I'll break there, which is actually the third law of thermodynamics. And the third law is boring. It doesn't really say anything really very interesting. Here, I'll start a new board. It doesn't really say anything very interesting. It actually largely validates the second law. Remember, the second law is the most important by far. So let me start with the first law. Energy cannot be created or destroyed. And I think that is why you can say that the change in U is the change in heat and work and why it's exact. And I'm actually not sure about that, but I'm pretty sure that's the validity of that statement comes from the fact that you cannot create or destroy energy. And okay, that's the first law. The second law, you can't turn all heat to work. And total entropy always increases. Two weird ways to state the same thing. It doesn't seem that way, but I know that it is. The third law actually just validates the second law, and it's all about measuring. That's the third law. The third law actually just gives us a way to measure entropy. And again, entropy is more important than anything, and those energy functions are just stand-ins for entropy because I don't have an entropy meter. So, the third law, now I totally don't get this. The third law is stated via Nernst's theorem. You might remember Nernst from some electrochemistry things when you had to calculate the potential of copper and zinc, a Daniel cell. You should have had that in freshman, hopefully. Let me make sure I spell it. Nernst theorem. Walther Nernst, he was kind of one of the more interesting people. Actually, I don't really have too many more interesting people, except Schrodinger, who had 2 wives. That's true. Nernst, he was a 1930s guy. He actually, more like 1800s. Towards the end of his life, he was in Germany dealing with you-know-who. But so he actually almost came close to inventing the first practical incandescent light bulb. He almost got credit for that. Remember that Edison just kept making them over and over again until he found one that practically worked. He didn't really come up with the idea. Where he is totally awesome is that he invented the electric piano, which is how Jimi Hendrix invented the electric guitar. So you owe it to him. It wasn't Jimi Hendrix, it was, who was it? Was it Les Paul that invented the electric guitar? He invented the most awesome electric guitar. Anyway, so that was Walther Nernst, and his theorem is how we define the third law, and this is how it states. Why do you define a law through a theorem? Why don't you just call it a third theorem? I don't get that. Anyway, when it said, and I've actually already told you this, I'm looking for it now. Oh yeah, here it is. A perfect crystal Okay, a perfect crystal at 0 degrees K has entropy of 0. Just want to remind you of units. Okay. Now, I've actually already covered this. Remember that when I showed you, and this is one of the reasons actually I like to cover this, I showed you that 3 chess pieces on a 3-piece board has only one way to exist, right? And that's actually the third law of thermodynamics. So that I actually was proving that theorem, so I guess that's a law now anyway. So this is where it comes from. And of course, what we're talking about is a perfect crystal of a chemical, like water. So to measure the entropy of water, what you do is you freeze it. You do it as carefully as possible so that it's a single crystal. That's sometimes possible, sometimes it's not practically possible. That's not an issue with the third law, it's an issue of practicality. Anyway, we take stuff, we freeze it very carefully until it's a perfect crystal, and then, if the third law is correct, which we're pretty sure, then it has no entropy. So what? Well, what happens next is that allows us to warm things up, measure the heat goes into it, and figure out what the entropy is. So let me write that down. But let me tell you the big point of this. So what? For one, it says entropy is real. This is why I keep saying that it backs up the second law. Its purpose is to validate the second law, because given that the entropy is 0 at 0 degrees K, it allows us to measure entropy. I'm about to show you how we do that. It allows you to measure entropy, and I contend if you can measure it, it's real. If you can measure it and it's real, and total entropy increases, then that's true, right? So it kind of validates the second law by stating that entropy is real, it's measurable, and therefore what's being said in the second law has to be correct. Okay, now, one thing about this is, and don't write this down, I already wrote it down, since we like to change temperature of stuff at constant pressure, as we try to figure out what the new G's are of reactants and products, you see, we need to know what their entropies are. And people figured this out way back around turn of the century. People figured out that knowing the entropy of stuff, water, O2, N2, proteins, everything, we need to know the entropy of everything. And we chose to measure it at 298 degrees K, right? Because that's practical. We chose to measure the entropy of everything at 298 because of relationships like this. Because then we were able to figure out how to make delta G's negative. And even if I'm not at 298, knowing what S is at 298, I can figure out what the S is of water, O2, N2 at 398 by the equations I just showed you, which is why we did all that. Okay, so again, I've got a starting point for entropy. Let me write down how the entropy of a stuff gets measured by a giant ass equation that goes on forever. Okay, and then here's a subtlety, by the way, and this is also a homework answer. When you look at those high school tables at the back of the book for, remember, all those chemicals, water, O2, N2, H2, CH4, blah, 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 and you look at the top, you have delta H, delta G, those are, we're going to cover those are enthalpies of formation, delta G's of formation, but you don't have S, delta S, you have S, not delta S of formation. No one calculates delta S as a formation. It's S, not delta S. It's not a relative, it's an absolute, and it's done this way. Okay, so we'll start at 0, but then again, that's 0 joules per K. Right? Again, the whole point is that I know what the entropy of something is at its starting point, and then I need to figure out what the heat over temperature is. Don't forget the fundamental equation for entropy is heat over temperature. Of course, heat doesn't exist, it's a changing heat, and to do that, what we're going to do is use, to get the changing heat, I'm going to measure that by heat capacity times changing temperature. And of course, that's over T. I've got a partial, it has to be integrated. And of course, I'm going to go from 0 to the meltdown. Everything's a solid at 0 degrees K, or this wouldn't work. Perfect crystal would automatically imply solid. And we're going to heat things up until they melt, which is defined merely as the fusion temperature. So melting in correct excuse me, in correct chemistry E's, melting is fusion. That's our IUPAC, remember that organization that standardizes all this stuff. IUPAC says the word fusion is the same as melting. Okay, so again, heat over temperature, I got a partial, it needs to be integrated. Now, I wrote Cp as a function of T to remind you that heat capacity is actually a function of temperature. We largely ignored that in this class, but sometimes you can. This is one of them. Okay, now you melt. Now I got to melt the thing. Now remember, this is being all done in a special calorimeter, and the calorimeter can be frozen to 0 degrees K. Calorimeters work really well. We have really great calorimeters. And when something is melting, I can measure the enthalpy of that process. And what's nice is that when something melts, the temperature doesn't change, so I don't need to integrate anything, all right? Okay, let's go on. Now I've got myself a liquid. And of course, the liquid forms, as I'm warming it up, it starts at the fusion temperature. It will remain a liquid to the vaporization temperature. And of course, liquids have their own heat capacity, which is still a function of temperature. Da-da-da-da-da. Okay, now liquids will eventually evaporate, which have their own enthalpy. Okay, now it's a gas. Okay, now the thing is I can keep going on and on and on until something's a plasma. And then at that point, I'm done. Right, then I'm talking about the S of the sun. Okay, so anyway, it just goes on and on like this. I'm not going to write the thing for the heat capacity for a gas, yada, yada, yada. Remember that we're actually going to make tables in the back of the book, and we're going to stop this process if something's a liquid, if the vaporization, like water, right? If the vaporization is higher than 298, I don't actually go past this, right? I go for water, I go to 273 to 298.15. It remains a liquid, and so none of this is there. If it's O2, then yes, then I need to let O2, of course, evaporate because it's a solid liquid gas. And then anyway, blah, blah, blah. Like it's high school level, all right? So let me graph that. And because one thing that's kind of important, and as I know I probably do it too much, is that I am prepping you for 344. I really believe you folks have stepped up since the first homework, and my read on your grades and your tests is I expect all of you to get to 344. As I kind of really went out of my way to mention that heat capacity is a function of temperature, I want to graph that for you. I want to show you what entropy looks like. Sometimes some textbooks actually show you just heat capacity and remind you that you're integrating it. I actually like to show you entropy as a function of temperature. And it looks something like this. Okay, so then what happens, here, I need to give myself some room. Okay, so entropy of a solid starts at 0. And of course you get to the fusion temperature, again, the melting temperature. And what happens is the entropy of stuff jumps. Right now, it makes sense. Something is a crystal. It's no longer a perfect crystal because it's shaking because it's warm. I then input heat, which is the same thing as inputting disorder to melt it. And you know liquids are more disordered than solids. And the entropy rises further now that I'm in the liquid state, up until the vaporization temperature, in which case I get a big rise in entropy, and then on and on and on and on and on. Now, I am kind of careful how I draw this. I've actually been, notice how this had a nice slope and this had a kind of a thin slope, because I want to remind you that entropy is proportional to heat capacity over temperature. So as temperature rises, entropy tends to rise not as much because it's being dulled by a higher and higher 1/T factor. It's a factoid, don't worry about it. But what I wanted to cover in this last bit is this right here. This region right here, this is actually how we discovered quantum mechanics, was that the heat capacity, so entropy is measured by heat capacity. What people discovered that entropy and heat capacity had this weird scaling of roughly T to the 3rd power. So I kind of tried to, I know it looks like a T squared, but I tried to draw it as a T cubed. You can't really tell the difference, right? This is actually how we discovered quantum mechanics. was because of this, because no one could model this with a theory until Einstein got close. I wasn't perfect. You're his cousin, I think. Anyway, so me and my friends were talking about that, making fun of him. And he's dead, so I don't know why we're doing that. He wasn't perfect. He actually did come up with a theoretical description of why entropy and heat capacity, same thing basically, worked like this at low temperatures. He didn't get it right. Another guy, Peter Debye, who is one of these central figures in quantum mechanics, comes up with a quantum mechanical answer for why this happens. So now remember, I can't emphasize this enough. You're integrating heat capacity to get entropy. You're integrating heat capacity. And heat capacity is all about degrees of freedom, right? So remember that heat capacity at constant pressure is the change in H with the change in T. H is basically U, and U is all about degrees of freedom. I know that was a little convoluted, but anyway. The way that Debye was able to describe this behavior was that he described it as, he figured out that solids are vibrating, right? Just, I'll draw it, I'll draw it in a minute. What it means for solids to vibrate. What he figured out was that there were a certain number of ways that you could vibrate. I looked this up on Wikipedia. The number of ways you can vibrate as a function of temperature kind of rises like this and then comes to a stop, which we call a Debye temperature. And you will, in your readings, occasionally see this word, and that's what I'm explaining what that means is. This is also called the density of states. And I'll explain what vibrational modes are for solids in a second. They're called, phonons. They're called phonons, but they're just vibrations. Now this is important again. This is density of states. Number of states is a function of basically energy. R times T is energy. And what Debye figured out was that that this has the scaling as like T to the 3, and that changes heat capacity. That changes your entropy. Look, I'm probably going crazy here, saying too much, but let me explain with the picture what is happening and how we discovered quantum mechanics. Why is this rising and why does it come to an end? So accept this. Accept that the way that the number of vibrational modes increases with temperature and comes to an end. Believe that, and then this is correct. All right, I know it's correct, we didn't measure it. Let me explain what vibrational modes are for a solid. Okay, solids have atoms in ordered positions, right? You know that. You're in organic with Cabana. Okay, so they have, you should have covered that anyway. I'll just draw a lattice. So it looks like I've got something, I'm kind of looking at it directly down the side, and there's this row of atoms. So I don't know what the space group is of this and all that, what the unit cell is, I don't care. But what's happening is that as I start to warm this up, it starts to vibrate. And what happens is, it's kind of like this. Vibration is motion, and I can represent that by a wave. Okay, so these atoms are kind of bouncing up, and these atoms are bouncing down. I won't do the bottom one, but anyway, you get the idea. Okay, so again, you know that temperature is motion, and I can represent the motion like a wave, right? This isn't hard to imagine, right? It's doing this. It's actually doing like this, right? And that's not hard to imagine. It's like a drum, right? Now, what happens is, as it gets more and more temperature, like you see, this is a very low energy. This is a low frequency motion. As it gets more temperature, it can eventually do this. All right, you see, as temperature rises, its frequency of motion can rise too, just like that. And then, of course, the lower ones. Anyway, you get my point. As temperature rises, it has new ways of moving which have different frequencies or different energies. So as you warm something up, the ways that it moves start from this very low energy to this, which is higher energy. It requires more heat to do that. It scales like T to the 3, which is why you get this behavior of entropy. But it comes to an end because you can't move at a higher frequency than a wavelength of one atom, right? You see that? How can I make this move with higher frequency and higher energy? I can't. I can't go beyond this. And that's why the number of modes comes to an end. Integrate this. It fits into here. It describes it correctly. This, by the way, is one of the fundamentals of quantum mechanics. So there you go. That's how we discovered quantum mechanics. So, sorry I'm blabbering.